Ah,
Then as a consequence, cosine of theta has to be x over 3. How do you invert this statement? If inverse cosine of x over 3 is theta, then cosine of theta has to be x over 3. It's like a zigzag. Cosine of theta has to be x over 3. By the way, we're going to assume that x will not cause any domain problems. So x, for example, could not be a number greater than 3. All right, cosine of theta equals x over 3. Now, we can use SOHCAHTOA and develop a right triangle model. SOHCAHTOA. We're going to set up a right triangle model so that cosine of theta is x over 3. Let's make this angle measure theta. SOHCAHTOA, ka. Cosine is adjacent over hypotenuse. And you can see that if you set up this right triangle model, then it's true that cosine of theta will be x over 3. Cosine of theta is adjacent over hypotenuse. And then, since we want to find the cotangent of this angle, remember, we want to simplify cotangent of theta over here, then it would help to find an expression for b, the length of this leg here in terms of x. I'm calling it b here. You could call it a or something else. It turns out to be the square root of 9 minus x squared. And how do we get that? Well, what theorem will relate these three expressions for the sides of this right triangle? The Pythagorean theorem. X squared plus b squared equals 3 squared. X squared plus b squared equals 9. Again, people might be tempted to isolate x squared or b squared on one side because they feel like it, but no, it's not that easy. X squared plus b squared equals 9. And we ultimately want to solve for b, which is buried in there. Sorry, but you're going to have to do some algebra. X squared plus b squared equals 9. First, let's isolate the b squared term. We accomplish that by subtracting x squared from both sides. On the left side, when you subtract x squared, you're left with b squared. On the right side, 9 minus x squared results on the right side. We're subtracting x squared from both sides. Now from the square root method, b can be plus or minus the square root of 9 minus x squared. And then when applying this method, it turns out that we can delete the plus minus symbol. You can analyze various cases to see why that's true. Here, we assume that theta was acute for our right triangle model, but it turns out that our right triangle model will work even if theta is not acute. We take b equals the non-negative root of 9 minus x squared. And we can label the side like so. Remember, to find cotangent of theta, it's going to be helpful to find an expression for this side length in terms of x. Again, what do we want? Cotangent of this angle theta. Now, it might be helpful to consider its reciprocal function first. What is tangent of theta? Tangent of theta, toa, in SOHCAHTOA, tangent of theta is opposite over adjacent. Tangent of theta is b over x, or the square root of 9 minus x squared over x. That's tangent of theta. But then, to get cotangent of theta, we have to take the reciprocal. Cotangent of theta is then x over the square root of 9 minus x squared. Cotangent of theta is x over the square root of 9 minus x squared. And we're done there. This is an algebraic expression in x. It's something we might have seen in chapters 0, 1, or 2. Think of the quadratic formula. We're allowed to have things like exponents, nice roots, things like that. Now here, a lot of students would try to rationalize the denominator. Actually, I don't recommend that. Generally speaking, this expression here would be considered simplified. If the radicand down here is variable, we actually tend not to try to rationalize the denominator. For example, if x is a messed up number, like the 5th root of 2 or something like that, then we would not be able to rationalize it easily anyway. Not easily. What if x is something like 1 over e? It's basically impossible. All right, so this is our simplified algebraic expression. By the way, the square root of 9 minus x squared is not 3 minus x. We do not take square roots term by term. So please do not try to simplify this to 3 minus x. Now I claim that this is our expression for cotangent of theta. It's a simplified algebraic version of cotangent of theta, where theta was all this inside here. So my claim is that this expression I have in blue here is equivalent to x over the square root of 9 minus x squared, as long as we don't have any domain problems. Well, let's verify this on Desmos. The original expression is here. Let's graph y equals cotangent of arc cosine or inverse cosine of x over 3. I'll turn that graph on, and it's this red graph over here. It turns out to have VAs, vertical asymptotes, at x equals -3 and x equals +3. That makes sense because if you look here, we know that we're going to be in trouble if x is something like 4, 5, or 6, then x over 3 would not be a cosine value. Likewise, if x were like -4, -5, or -6. Even if x is 3, for example, then we'd get inverse cosine of 1. Inverse cosine of 1 is 0, and it turns out cotangent of 0 is undefined. That corresponds to the VA at x equals 3. Likewise, at x equals -3, we also have a VA. It turns out that the domain for this expression, this function, is going to be the open interval from -3 to +3. Well, guess what? Look at this expression that we're claiming is equivalent to the given expression here, x over the square root of 9 minus x squared. Using the methods from chapter 2, section 2.7, the domain for this expression or function is, again, the open interval from -3 to 3. Notice that at x equals +3 or -3, we're going to end up with a 0 denominator. That corresponds to the VAs at x equals -3 and x equals +3. Again, my overall claim is that this expression, this algebraic expression, is equivalent to the given trig and inverse trig expression. Let's turn on the corresponding graph and see if this red graph just recolors. Yes, it does. The purple graph is the same as the red graph. You can see this flashing, which means that these equations are equivalent and these expressions on the right sides are equivalent. This is not a proof, but it's a very convincing and gratifying check. The fact that these two graphs are the same. Now, I'm not just playing with you. You're actually going to have to work out and simplify expressions like these in your Calc 2 class, Math 151. Because in Math 151, there's a technique called integration using trigonometric substitutions, where you actually have an integral problem and you want to use a trig sub like cosine of theta equals x over 3. And at some point, you have to unravel an expression like this and rewrite it algebraically. You actually do that in a Calc 2 class. So you will see this later on in your calculus adventures. Next up, we're going to talk about how to use inverse trig functions to solve equations. Next time.
All right, any questions thus far? That's a specific type of problem. Yeah, a question about the domain. For example, why is the domain of this algebraic? Okay, so when is that real? Okay, so it's real if and only if 9 minus x squared is positive, right? So imagine a parabola, right? So, okay, take y equals 9 minus x squared. All right. Where's that non-negative? It's non-negative between -3 and +3. Between -3 and +3. So this here, the radicand is only positive between -3 and 3.
Hi, everyone. We're going to
Okay,
go back to section.
Okay. All right. Anything else? Any questions? Okay.
Hi, everyone. We're going to go back to sections 4.2 to 4.4 and do some of the parts we skipped earlier. In part F, we're going to talk about how we can use inverse trig functions to solve an equation like this. Sine of theta equals 0.4. Now, I need to make a point first, and I'm going to go all the way back to factoring from section 2.5. So in section 2.5, let's say that you run into your old algebra teacher in a dark alleyway, and your old algebra teacher asks you to factor x squared minus 3. Now, you should ask your algebra teacher over what set? And then maybe your algebra teacher will dissolve and disappear, because the answer will differ depending on what set of coefficients will be legal. If you try to factor this old school over the integers, like you may have tried to do in your old algebra class, guess what? X squared minus 3 is prime over the integers. You cannot break this down any further if you're only allowed to use integer coefficients. But if you're allowed to use the whole swath of real coefficients, if you're factoring this over R, the set of real numbers, this does break down. You can think of this as a difference of two squares, and this factors as, remember, x plus root 3 and x minus root 3. So you see, the answer to this factoring problem depends on what set you're allowed to factor this over. What are the coefficients that you're allowed to use? Well, likewise, when we asked, how do you solve sine of theta equals 0.4? You need to ask on what interval. On homework or exams, I hope to make that clear. Now, in general, if you're asked this on a general test, then we assume that you want all real solutions. But for now, let's be careful about the interval of values for theta that we're really looking at. So you want to ask on what interval. Solve this equation on what interval. That is, on what interval of values for theta. These potential solutions for theta. Okay, first off, let's solve this trig equation on the open interval from 0 to pi over 2. In other words, we're going to find the acute solution or value of theta that will make this work. What is the only acute angle in radian measure such that sine of theta equals 0.4? There's going to be one acute solution here. Remember, your answer to a solve an equation problem is a solution set, and I claim that you will only get one acute solution. We will have a solution because 0.4 is a legitimate sine value. It's in the range. If we had a 2 or a 3 here, then the solution set would be empty. But here we will have one acute solution. Well, let's look at the unit circle. Let's look at the unit circle. All right. On the unit circle, remember that sine of theta corresponds to y. Sine of theta corresponds to the y coordinate on the unit circle. Now, where on the unit circle is the y coordinate, the sine value, equal to 0.4? Let's say over here and over here. So in general, there will be solutions to this in quadrants 1 and 2. But wait, we only care about solutions in this narrow interval. We only want the sole acute solution to this equation. So we only want the acute angle, the acute representative for this point over here. Sine of theta equals 0.4 has only one acute solution, this angle. We want this measure for theta. And how would you calculate this on your calculator? How would you find the measure for this acute angle? Well, it depends if you're in degree mode or radian mode. Make sure you're aware of what mode you're in and how to go back and forth between the modes. But it turns out that if you're in degree mode, when you work out the inverse sine of 0.4, and that's what you have to calculate, the inverse sine of 0.4. We have to calculate the inverse sine of 0.4. The inverse sine or arc sine of 0.4, which we know will be an acute angle. Now in degree mode, we're going to get 23.6 degrees. In radian mode, you're going to get 0.412 radians. Now let's check to see that this makes sense. So I'm claiming that over here, the corresponding angle will be about 23.6 degrees or about 0.412 radians. And remember that the y-coordinate, the sine value, is 0.4. Well, it makes sense that the angle here is less than 30 degrees because for 30 degrees, I'll put that in purple, for 30 degrees, this might be a bit too steep for 30 degrees in reality, but for 30 degrees, remember that the sine of 30 degrees is 1/2 or 0.5. I hope you remember that. The sine of 30 degrees is 0.5. Well, if the sine of 30 degrees is 0.5, if this is 0.5 up here, I know it's not to scale. If the sine of 30 degrees is 0.5, it makes sense that the sine of a smaller angle, in this case about 23.6 degrees, will be 0.4. And 0.412 radians will be a bit less than pi over 6 radians, which was 30 degrees. Okay, so this answer makes sense. If you're asked to find the acute solution for this equation, remember the answer to a solve an equation problem is a solution set. There's only one solution that's acute, and it's about 0.412 radians. I'm going to use radian measure here. Although when answering a problem, make sure that you're answering using the appropriate unit, whether it's degrees or radians. What is it you're asked for? The hard part is not going between degrees and radians. The hard part is knowing what to do. How many solutions do you have and where are they? So this equation only had one acute solution. But now let's ask a second related problem. What are the solutions to this equation on this interval, basically between 0 and 2 pi? That is, find the solutions, values for theta, around one classic revolution around the unit circle. I have a parenthesis here because, remember, 2 pi is coterminal with 0. All right. So let's see what happens there. Between 0 and 2 pi. So this time, we're going all around the world once. In terms of looking for solutions, we're going to look around the unit circle in terms of looking for solutions. From 0 to 2 pi. What are the solution values for theta we pick up? Now again, we want to find angles whose sine value is 0.4. And actually, I can appeal to this picture back here. Again, we're looking for 2 points whose y-coordinate is 0.4. I should probably lower this a bit. 2 points whose y-coordinate is 0.4. All right. So between 0 and 2 pi, how many angles are we going to pick up? As we go around the world, as we go from 0 all the way around to 2 pi, not quite 2 pi, what angles do we pick up? Well, we pick up the same acute angle that we did before, the whole 23.6 degrees or 0.412 radians. In fact, I can copy this. So we get this acute angle over here, but wait, we also have this supplementary angle over here. It's a brother, a coreference angle. They have the same reference angle, namely this. Now, how can we get a measure for this supplementary angle in quadrant 2? Well, in degree mode, you would do half a revolution, 180 degrees, minus the reference angle, which was the 23.6 degrees. So the supplementary brother in quadrant 2 that we want will be about 180 degrees minus 23.6 degrees. That's about 156.4 degrees. So in degrees, that's going to be this degree measure for this solution. In radian measure, you use pi radians. Instead of 180 degrees, you use pi radians to represent the half revolution. Pi minus 0.412 is about 2.730 radians. So again, in quadrant 2, the solution that we want will be about 156.4 degrees, or about 2.730 radians. I have the right to put that 0, so I'll put it in. I'm going to put these out to 3 decimal places. All right. So in radian measure, our 2 solutions will be about 0.412 radians and about 2.730 radians, this quadrant 2 angle, which is still between 0 and 2 pi. It's obtuse. So in solution set form, if we want the solutions between 0 and 2 pi, there are 2 of them. One is about 0.412 radians, that's the acute quadrant 1 solution, and one is about 2.730 radians. That's the obtuse quadrant 2 solution. And this kind of analysis will help you on the homework. It's harder when this value over here is negative. Then you really have to think. When in doubt, think about the reference angle. So even if the reference angle itself is not a solution, it's still a good thing to build things off of, because it's easy to get from the reference angle to key brothers in the other quadrants, whether you're in degree mode or radian mode. Now here's a preview of chapter 5, namely section 5.3. Solve sine of theta equals 0.4 on R, the set of all real numbers. Let's find all real solutions. That's going to be a chapter 5 problem. So what do we pick up? Well, as we go around the world, we pick up our 2 solutions from before, from question 2, but we're allowed to go around and around and around and around, both counterclockwise and clockwise. So we want not just these 2 solutions, but all of their coterminal twins. So we want this, also this, plus 2 pi, plus 4 pi, and so forth. Also minus 2 pi, minus 4 pi, and so forth. We want this obtuse solution, and also this guy plus 2 pi, plus 4 pi, and so forth, and minus 2 pi, minus 4 pi, and so forth. So we can take these guys and add or subtract integer multiples of 2 pi. This is how we'll write our approximate solution set in chapter 5. It's this long thing. The solution set is the set of all theta in the reals such that theta is about 0.412 plus 2 pi n, where n is integer, or theta is about 2.730 plus 2 pi n, where n is integer. Again, we want this acute solution, and also all the coterminal twins. N can be negative as well, a negative integer. Also, we want 2.730, this obtuse solution, and also its coterminal twins, where n could be 0, a positive integer, or a negative integer. So in chapter 5, and specifically in section 5.3, we're going to solve trig equations on R, and we're going to get all real solutions. Typically, we'll get infinitely many solutions. Sometimes, like for sine of theta equals 2 or 3, we'll get the empty set. You'll get lots of practice on the homework. So that's section 4.7, including a rollback to 4.2 to 4.4. Next, we'll discuss word problems.
Okay, before we get to the word problems, questions about solving these basic trig equations. That's going to help on the homework, and it's a good preview for chapter 5, actually. Any questions? Any questions? Let's do a bit on word problems.
Hi, everyone. Let's do a word problem. We're still in the 4.2 to 4.4 block. This is the last part there. Part G, a word problem. So for example, a 6-foot-tall man like me, shut up, standing on a flat surface. So it's good to draw a picture. That's a key trick for these problems, drawing a picture. So a 6-foot-tall man, right? The 6 feet is here and also over here. And these are in feet, by the way. Standing on a flat surface as opposed to an incline. So word problems, sometimes it's tricky to state them precisely. So this man is standing on a flat surface, not a hill. And he's looking up at a 20-degree angle of elevation. Now, I'm kind of assuming that his eyes are on the very top of his head, so we're kind of ignoring the forehead. But he's looking up at a 20-degree angle of elevation, okay, up towards the top of a flagpole. So here's our flag being patriotic, right? Okay. Well, our flagpole is here, right? Our flagpole is over here. His feet are 70 feet away from the base of the pole. By the way, if you want to put a unit, that crit mark can stand for feet. Okay, let's see. His feet are 70 feet away from the base of the pole. And we have a right angle here because, again, it's a flat surface, not a hill. How tall is the flagpole? And we're going to denote the height of the pole by x. And that's going to be in feet. Now, sometimes the answer is not going to be x. For example, when we set up this right triangle problem, some people might want x to be the actual side of the right triangle here, and then the answer would be x plus 6 in feet. But the way I'm setting it up, x will represent the answer in feet. Okay, now, the man is 6 feet tall. So we have this rectangle down here that's 70 feet by 6 feet. And on top of the rectangle, there's a triangle. Now, the overall height of the pole is x in feet. We have 6 feet corresponding to this height, this line segment. So this side of the triangle is given by x minus 6 in feet. And we're going to use that as part of SOHCAHTOA. X minus 6 is the length of this leg for the right triangle. Okay, so we ultimately want to solve for x. We have an angle. We have the adjacent side, it's 70 feet. We want to know about the opposite side. So what trig function relates an angle, the opposite side, and the adjacent side? It sounds like TOA, SOHCAHTOA. Sounds like a tangent problem. All right, tangent of 20 degrees is opposite over adjacent. X minus 6 in feet, so x minus 6 in feet over 70 feet, which means that the feet units will cancel out. The top is in feet, the bottom is in feet. Tangent of 20 degrees has no unit. It's a strict ratio. Tangent of 20 degrees is x minus 6 all over 70. We want to solve for x. First, let's get rid of the 70 on the right side. we're going to multiply both sides by 70. Time for some algebra. 70 times tangent of 20 degrees equals x minus 6. And then to solve for x itself, we're going to add 6 to both sides, 6 feet. So, and now I'll turn it around. X equals 6 plus 70 times tangent of 20 degrees. 6 is in feet, 70 is in feet. Tangent of 20 degrees has no unit. X will be in feet. Now be careful, don't add 6 and 70. We do not get 76 here. A scientific calculator should know that the product comes first. And make sure your calculator is in the appropriate mode, degree mode. 20 is in degrees. So make sure you're in degree mode. We get to the nearest tenth of a foot, about 31.5, and we should put a unit, feet, because these were in feet. It's a consistent unit. Nowadays, more and more, it's good to write down the final answer using proper English sentences. The flagpole is about 31.5 feet tall. That was the question. What is the height of the flagpole? It's about 31.5 feet tall. All right. Once again, if instead, I'll put this in purple. If instead the height of this triangle were x in feet, then the height of the pole would be what? X feet plus 6 feet. Well, that's going to be x plus 6 in feet. Which means if you were to make the height of this triangle x, then your answer, the height of the flagpole, would require you to add 6 feet. So make sure that you get the height of the flagpole. Your final answer may not be x. If you make this x, your answer will be x plus 6 in feet. But we set it up here so that x is the height of the pole. The flagpole is about 31.5 feet tall. Again, remember the units in your final answer. And try to avoid approximating until the very end. Many people are tempted to round off things right in the middle, but then you're in danger of losing accuracy. It is good to try to keep things as exact as possible along the way, like we did for logs back in chapter 3. If you do round off, make sure you use many significant digits just to be safe. Okay, in section 4.8, I discussed some general principles for word problems, but really you have to practice them. In fact, when you actually practice these word problems, the hardest part for many students is figuring out which side is which length. So they're doing a word problem and students aren't sure. Well, is this value this leg? Is it this leg? Or is it the hypotenuse? And that depends on the word problem. That's hard to teach. You get it from practice. But what are some general principles for word problems? First of all, well, read the problem carefully and highlight as appropriate, underline or highlight, in case you have to keep going back to some information. Define variables, like you might say, let x be the height of the flagpole. Draw a diagram and label them. Sometimes that's a decent substitute for this, but technically you should always define your variables, preferably in words. But diagrams help a whole lot. If anything, the diagram is more useful to a student. In calculus, by the way, you'll need to keep track of which aspects of the problem stay fixed or constant and which aspects change. For example, in ladder problems, let's say we have a ladder leaning up against a wall, and it's on the flat ground here. The length of the ladder tends to stay constant, but this leg here and this leg here can vary as the ladder slides around. So in calculus, you have to keep track of what stays constant and what changes. Y and X could be changing, but this could be a constant, like 15 feet. Make appropriate unit conversions where appropriate. So for example, if Y here is in inches and X here is in feet, then you have to convert from one to the other. They both have to be in inches or they both have to be in feet. It's one or the other. They have to be consistent. They can both be in inches or they can both be in feet or even some other unit, as long as you're consistent. So make sure you get to 1 unit. Sometimes the problem will give you red herrings, numbers that don't really matter. For example, if I say in the year 2020, this happens, you probably won't need the 2020. So ignore red herrings. They're there to trick you. Make sure you clearly answer all the questions you are asked. Answer all the questions you are asked. Okay? And sometimes X does not represent the final answer. So for example, in our flagpole problem, if X is just the length of this leg, then X plus 6 in feet is the height of the pole. That's what you would really want. Sometimes X is not your final answer. Now, in a math class, you're expected to give exact answers, but in word problems, you might be asked to round them off. So be aware of what the question is asking for. So again, in math class, we expect exact answers, but in word problems, we're often asked to approximate or round off and follow the instructions in the word problem. If you do round off, use many sig figs just to be careful. In your final answer, write units where appropriate, like feet in our example. And in fact, we tend to prefer complete sentences nowadays. See if your answer makes sense. So if I claim here that this flagpole is 1,000,000 miles high, you probably made an error. I would bet that you made a conversion error. For example, maybe you should have converted from inches to feet or vice versa, and you didn't do that. Again, be prepared to write your final conclusions using plain English sentences. In these days of Common Core, we tend to prefer that. Okay, so those are some principles of word problems, but the bottom line is you have to practice them. I'm going to discuss techniques that are specific to right triangles in the next video.
Okay, so you just need practice on the word problems. In the next video, I'm going to talk about how you analyze right triangles, how you really tear them apart. Any questions before we go on to right triangles specifically? All right.
Hi, everyone. We're going to solve right triangles. So you could say that a triangle consists of 6 parts, 3 angles. For a right triangle, one of them is a right angle, and 2 complementary angles that add up to 90 degrees. And also 3 side lengths, which we could label little a, little b, and little c for the hypotenuse. When we solve a right triangle, we're given some of these parts, and we have to find all the others. In a word problem, you might just want to find one of these parts in the end. Now, what will relate these various parts? Well, we have 3 tools that we can use. What relates the 3 side lengths of a right triangle, A, B, and C? Well, A squared plus B squared equals C squared. That's Pythagorean theorem. That relates the side lengths. The Pythagorean theorem. What relates the angles? Well, the interior angles for any triangle, not just a right triangle, must add up to 180 degrees. So that's a rule for the angles. And what will relate side lengths and angle measures, sides and angles? SOHCAHTOA. For example, sine of theta is opposite over hypotenuse, and so forth. That relates angles and sides. So this 180 degree sum rule for angles, the Pythagorean theorem for the side lengths, and SOHCAHTOA, which relates angles and side lengths, these are 3 key categories of tools that we're going to use. For example, let's solve the triangle below. I'm giving you that we have a right angle here. This leg is 7 feet, and the hypotenuse is 9 feet. And by the way, this is the conventional way to label a right triangle. Capital A and capital B represent the acute angles, or their measures. Angle C is the right angle. And then the side lengths are labeled little a, little b, and little c. The side with length little a faces or is opposite to angle big A, and so forth. Little b is opposite to big B, little c is opposite to big C, the right angle. So little c is the hypotenuse. This is a conventional way of labeling a right triangle. By the way, convert units as necessary. If, for example, I had given you 84 inches for the length of A, you may want to convert to feet. You'd have to make the units consistent. All right. Now, first of all, I'm giving you the right angle here and two side lengths. Now, what's missing? What do we need to find? We need to find the length of little b, and we need to find the measures of angle A and angle big B. I'll double circle these. We need these two angles and this side length. Okay. Now, again, given these two side lengths, how can we find this missing side length on a right triangle? The Pythagorean theorem. A squared plus B squared equals C squared. I'll do the calculations over here. All right, A squared plus B squared equals C squared. So, and these are consistent units, feet. 7 squared plus B squared equals 9 squared. 40, and now, bear in mind, the B or B squared is buried in there. Don't engage in wishful thinking and isolate B squared immediately. You'll probably make a mistake that way. The B squared is buried in there. Let's isolate the B squared. We do that by subtracting the 49 from both sides. Remember, 7 squared is 49 and 9 squared is 81. 49 plus B squared equals 81. Let's subtract 49 from both sides. B squared equals 81 minus 49 is 32. Square root method, B equals plus or minus the square root of 32. But because we have here a right triangle, we have no funky things going on with quadrants, we take the positive length. So we take B equals positive root 32. Let's simplify that. The largest square that divides 32 nicely, the largest perfect square, is 16, and the 16 pops out as a 4. Root 32 is root 16 times root 2. Root 16 is 4. So B is exactly 4 times the square root of 2 in feet. Right. So B will be 4 root 2 in feet. 4 root 2, by the way, if you approximate this on a calculator, well, root 2 is about 1.4, so I know that this will be about 5.6 feet. All right. Now, we now have all three side lengths for this right triangle, and we know that big C is a right angle. How can we find these two other complementary angle measures? For example, what if we want the measure for angle A? Well, let's see now. At the beginning, I was given that the opposite side was 7 feet. That's the opposite side relative to angle A. And the hypotenuse for the triangle was 9 feet. At this point, I could even use the fact that the adjacent side is 4 root 2 feet, but we might want to avoid that, especially if you're rounding off. So what trig function will relate an angle, the opposite side, and the hypotenuse? That sounds like the sine function. Sine of A equals opposite over hypotenuse, 7 feet over 9 feet, or just 7/9. Sine of A equals 7/9, and I know that A has to be an acute angle. So A itself has to be the inverse sine of 7/9. I'm sure we'll want to round that off. In degrees, it's about 51 degrees. And for these applied problems, when we're solving a right triangle, for example, we tend to use degrees. A is about 51 degrees. It's the acute angle whose sine value is 7/9. So this here is going to be about 51 degrees. Now for angle B, we could use SOHCAHTOA again, but let's do something even easier. Remember, the two acute angles of a right triangle are complementary. We're basically using the 180 rule for triangles in general. 90 degrees will be taken up by angle C. So angle A and angle B have to add them to 90 degrees. They're complementary. So we subtract 51 degrees and 90 degrees from 180 degrees, or just subtract 51 degrees from 90 degrees. Either way, remember angle B is the complement of angle A. Either way, angle B will have measure about 39 degrees. Be careful because many students might say 49 degrees because they might think percent. It's true that 51% plus 49% is 100%, but we're thinking degrees here. 51 degrees plus 39 degrees is 90 degrees. So be careful. We want these to add up to 90 degrees, not 100 degrees. You're thinking 100% then. Okay, so this here, angle B is 39 degrees to the nearest degree. So this all makes sense. These all add up to 180 degrees. The interior angles all add up to 180 degrees. And check this out. The eating rule checks out. I call this the eating rule. The idea being that larger angles eat or face longer sides. The largest angle here is the right angle, 90 degrees. The right angle must be the largest angle in a triangle. It faces the hypotenuse, the longest side, 9 feet. The medium angle here is 51 degrees. It faces the medium side, 7 feet. The smallest angle, 39 degrees, faces the shortest side, which turns out to be about 5.6 feet. If you had gotten something like 10 feet or 56 feet, you know you made a mistake. Also, there is something called the triangle inequality. Which basically says that a detour cannot be shorter than a straight length. So for example, 9 feet has to be shorter than 7 feet plus 5.6 feet because this represents the straight line segment distance. The detour here must be longer. So you must satisfy the triangle inequality. So again, this could not be 56 feet. So if you accidentally put the decimal point over here, you know this cannot be 56 feet because 9 feet plus 7 feet gives you a shorter detour, 16 feet. That cannot happen. So these are some basic checks. They're not necessary, but they're basic checks just to make sure that your answer makes common sense. It's good to check to make sure your answer makes common sense. So we've solved this right triangle. We now have all 3 angle measures and all 3 side lengths. Part C is optional. These are other ways that you can measure angles or directions. So for example, if you're going in this direction, you might say that a boat, say, is going 30 degrees east of north. So this ray here makes a 30-degree angle with due north. Again, that will not be on the homework or exams. In air navigation, you might take due north as 0 degrees and measure clockwise. So this southeasterly direction may correspond to, say, 150 degrees clockwise from due north. But again, Part C will not be on homework or exams. And that is Chapter 4.
All right. Any questions before we do a final bit on a review of identities? Any questions? We just have a little bit more to go, and then I'll take general questions or homework questions. All right, let's finish this part up. And then after this, you can go up through 5.1, number 1, if you're following the lecture.
Hi, everyone. We're going to solve right
Okay,
triangle
let's go.
in homework or exams. And that is chapter 4. Hi, everyone. We're going to start chapter 5 on analytic trigonometry. We're going to marry our two favorite subjects, algebra and trig. In section 5.1, we're going to review and apply the fundamental trig identities. There were five categories of identities that we looked at in chapter 4. The reciprocal identities. For example, what's the reciprocal of sine of x? It's cosecant of x, not secant of x. Make sure not to mix these up. And you need to know these identities left to right and right to left. The quotient identities, where we expressed tangent of x and cotangent of x in terms of sine of x and cosine of x. The Pythagorean identities, these three identities that involved the squares of the 6 basic trig functions. Sine squared of x plus cosine squared of x equals 1. We can divide by sine squared of x on both sides to get the second identity, and divide by cosine squared of x to get the third identity. Some ways to remember these. Remember that the up u, down u guys squared are all alone on the right side. And also on the second identity, remember that these co-guys go together. That's one advantage to having the reciprocal of sine of x be cosecant of x. The cofunction identities, there were many of these. Bottom line, cofunctions of complementary angles are equal. And the even odd or negative angle identities. Remember that cosine is even, and so is its reciprocal function, secant, meaning that these -1 factors on the arguments here, they can die. Cosine of opposite x equals cosine of x, same for secant. But for the other 4 basic trig functions, they're odd. So these negative signs basically pop out. These -1 factors on the arguments basically pop out and can become coefficients. So we need to remember and be able to apply these identities. Now, what do we mean by simplifying? Well, basically, we want to make these expressions more compact. So, for example, we'd want to replace 1 over sine of x with cosecant of x. There is no golden book for simplifying, but generally speaking, we want to make expressions more compact. Follow the conventions on the notes and the homework. You'll get used to it. So, how can we simplify trig expressions? There are many strategies. One strategy is to break things down into sine and cosine, kind of like taking change. If you're doing change, maybe you want to break things down to pennies and nickels. Sine and cosine, that's like pennies and nickels. And then we might be able to combine things and build things up. All right, let's simplify sine to the 4th x times cotangent to the 4th x. Well, let's see. We can break apart cotangent of x. By the quotient identities, cotangent of x is cosine of x over sine of x. So by the rules of exponents, it's true that cotangent to the 4th x is equal to cosine to the 4th x over sine to the 4th x. This does work. The exponent is shared on the top and the bottom. So when we replace cotangent to the 4th x by that fraction, what happens? Look here. Sine to the 4th x divided by itself is 1. Let's put little ones here. That's a good habit. And the result is cosine to the 4th x, which is simplified. So for example, if we wanted to know the value of this when x is pi over 3, instead, we can just plug in pi over 3 here. Cosine of pi over 3 is 1/2. The 4th power of 1/2 is 1/16, which is the value of this expression at pi over 3. But be careful. Actually, this expression does not hold for 0, pi, 2 pi, and so forth, because remember, there's a hidden restriction here. Sine of x, when that's 0, the expression up here is undefined. And in fact, we're supposed to have this restriction here. Sine of x cannot be 0. So if we wanted to be totally precise, we should make a note that sine of x is not 0. Admittedly, in chapter 5, we sometimes get a bit sloppy when it comes to matter of domains and hidden restrictions. But actually, if x equals 0, the expression here is undefined. The answer is not 1, which is what would happen if you try to plug in 0 here. But basically, for values of x that do not make sine of x equal to 0, the expression up here will be equivalent to the expression over here. And we can use Desmos to help check that for us. Let's graph y equals this, and then y equals this. So on Desmos, we have here y equals sine to the fourth x. It turns out that you need to type it in like this. Desmos will not accept sine to the fourth. You need to type it in as the fourth power of sine of x, times you would type out cotangent to the fourth x as the fourth power of cotangent of x. What's the graph? It's this. Although, as I mentioned before, this function or expression here is undefined whenever sine of x is 0. For example, when x is 0, pi, 2 pi, and so forth, the integer multiples of pi. Technically, we're supposed to have holes here. For example, at 0, 1, there's supposed to be a hole. But Desmos does not admit that unless you actually try to click on the point there. And then Desmos notes, hey, wait a minute. There's a hole here at 0, 1. There's a hole here at pi, 1. Can we get that? Maybe not. So Desmos is not so good at identifying holes. But there are technically holes at x equals integer multiples of pi. Again, this will not be a key stress in this chapter. What happens if we graph y equals cosine to the fourth of x? Y equals cosine to the fourth x. We get the same graph. Let's flash it. We get the same graph. Not a proof, but this is very gratifying. It makes us feel very confident that these two expressions are equivalent aside from the hidden restriction issue. The graph of this does not have any holes on it. The graph of this does have holes. So to make these truly equivalent, you need to put in that restriction that we do not allow values of x that make sine of x equal to 0. But basically, these two expressions are equivalent. That helps a lot. For example, if you want to take derivatives or integrals in calculus, you'd rather work with this guy than with this guy over here. So simplification is your friend, very often in calculus. We'll discuss other techniques for simplifying later on.
All right. Well, you can watch The Simpsons later on, but okay. So let's call that a day in terms of the new material. You can go up to you go up to 5.1 number 1 if you're following the lecturing. All right. All right. So homework due next week. Any general questions before I take specific questions?